Hello there, this is Jude Socrates, and welcome to video number 13 in my video series for multivariable calculus, known as Math 5C at Pasadena City College. So today we are going to look at double integrals using polar coordinates. Now, it's actually a rather long topic, so I am planning on dividing it into 2 or 3 videos. So I will see you at page 24 of our PDF, and I'll show you what I plan to do for this video. All right, so I zoomed out just so we can see the big topics that we're going to look at. So we'll start by looking at the polar coordinate system in GeoGebra. I'm going to show you how to navigate through that. And then we will plot a few points. We will specify some coordinates and we will plot them out in GeoGebra. We're going to learn how to convert between Cartesian coordinates x, y, and polar coordinates r and theta. So this part you might remember from pre-calculus or calculus 2 when you did areas bounded by some polar curves. So we are also going to construct what are called polar rectangles. And that's probably where we will stop in this video. And we will most likely need at least one more video to complete the concepts. So we're going to go to GeoGebra now and play around there. All right, so green. So what you do is you right-click anywhere on the grid, and that will give you the graphics menu. The options are at the bottom, okay, settings rather. So click on that, go to grid, and under grid type, drop this down and you will see polar. All right, so there it is. There is our polar coordinate system. So the circles, the concentric circles here, and the angles made by these rays are controlled by these two boxes. So check on this, and you can change these circles. For example, you can go to, let's say, 2, and then what's going to happen? Some of those circles disappeared. So now we go 2, 4, 6, and so on. Okay. You can create more circles if you want to. So for theta, you can do pi over 8, for example. And then you're going to see, okay, there we go. So it's pi over 8, pi over 4, 3 pi over 8, and pi over 2, and so on. Okay, so let's close this. Okay, so parts of the coordinate system. Okay, so we still see both the x and y axes here, but when we do polar coordinates, what's really important is the origin, which is now called the pole, and the positive x-axis. Okay, so that's called the polar axis. Okay, we don't really need the y-axis. We don't need the negative direction either. Okay. So that's our setup. So now I'm going to show you how to plot some points. Okay, so we're going to plot some points now. And the main thing to keep in mind is we're going to use a semicolon instead of a comma. Okay, so it's going to be, you will make that mistake in the beginning. I still do. Okay, so parentheses, 3 semicolon pi over 4. Okay, so there is our first point. Press enter. Okay, so there, labeled point A. So obviously, okay, so that angle is pi over 4. And of course, we use the polar axis as the reference direction for our angles. Okay, start measuring from there. Go counterclockwise by pi over 4. Okay, couple more. Okay, so how about 4 semicolon 2 pi over 3. Okay, so there we have our second point. You can also have a negative angle. Okay, so this time you go in a clockwise direction. Okay, so let's say we have 3 semicolon negative pi over 2. Okay, so there we are. We are on the y-axis. Okay, you can still call it y-axis. Okay, nothing wrong with that. Okay, what if you want to be on the x-axis? Well, in that case, then theta has to be 0. Okay, so we can have a point, for example, 6 semicolon 0. Okay, so in this case, 6, 0 is also are also the coordinates in x and y. Okay, and that's because when theta is 0, you are on the x-axis. What about if r is 0? Okay, so we can have 0 semicolon pi over 6 and boom. Okay, we are of course at the pole. Okay, so it doesn't matter what angle we use for theta. As soon as your r is 0, you are at the pole. Okay. All right. So okay. So what about the negative x-axis? Okay. So in that case, the angle is pi. So we can enter that point, a point there, let's say as 4 semicolon pi. Okay. So there we go. That is on the negative x-axis. All right. So we had negative values for theta. Okay, just go clockwise instead of counterclockwise. So what about if r is negative instead of theta? Or what if both are negative? Okay, so one at a time. Let's say we had negative 3 semicolon, what haven't we used yet? How about pi over 3? Okay, so here we are. Okay, so where did that come from? Well, pi over 3, of course, is somewhere up here. It's not marked off because our grid is in pi over, what did we say? These are pi over 6s, right? I'm sorry, pi over 8. So that's pi over 8, pi over 4, 3 pi over 8. So pi over 3 is somewhere over here, okay? So the negative 3 reflects the point in the opposite direction. Okay, in other words, add pi, or if you like, subtract pi. Okay, face the opposite direction. Okay, and that is where you plot the point. Okay, so with that, how can you produce point F? Okay, instead of 4 pi, we could also have put it as negative 4 comma 0. Okay, so yeah, whether r is positive or negative, if the angle is 0, you have a point on the x-axis, and it's written in the same way as we do in Cartesian coordinates. Okay, not so much on the y-axis. Okay, so we have point C over here, which we made with a negative angle clockwise by pi over 2. How can we plot point C using different coordinates? Okay, so we can use pi over 2 instead and then go backwards. So we will have negative 3 comma pi, almost, semicolon pi over 2. Okay, and check it out. I got away with it. See how D turned to, now it's called I. I got away with it in H because, of course, it's the same point whether it's comma or semicolon. So, semicolon and absolutely no change. Okay, so that is actually a good mistake. All right, so yeah, okay, so we can of course move this around as usual. Okay, how about both negatives now? Okay, so how about negative 4 semicolon negative pi over 4. Ooh, okay, so there we are, point J, negative pi over 4, go clockwise, and this angle is pi over 4, as usual, and we go backwards in the opposite direction by 4. Okay, still think of it as a distance of 4. Okay, so what's another way to get there? How about the angle will be 3 pi over 4, and then our distance, our r, will thus be just positive 4. Ooh, okay, so there is k. All right, k and j are exactly the same point. There's k, and now there's j, exactly the same point. All right, so let's talk about the conversion formulas. Okay, so it's really just nothing but trigonometry. We have a point here with polar coordinates r and theta. What are the Cartesian coordinates? Okay, well, theta is the angle formed by the line segment from the origin to that point. Okay, and of course, the length of that line segment is our r. Okay, now r could be negative, of course. So let's pretend that theta and r are both positive, and we're in the first quadrant. Okay, just for simplicity. Okay, so the x from trigonometry is, of course, just r cosine theta, and the y is just r sine theta. Okay, so let's see what happens if theta is in the second quadrant. Okay, so in this case, of course, and we keep r as positive. Okay, so in this case, cosine theta will be negative and sine theta will still be positive. So the formula is still correct. Okay, so now you might be worried, well, what if r is negative? Okay, so let's keep theta as this angle, somewhere between 0 and pi over 2. And now r is negative. Okay, so we're going backwards. Okay, so theta is still in the first quadrant, so cosine theta and sine theta are still positive. Okay, but if r is now negative, when you multiply by r, x and y become both negative. Okay, and is that correct? Yes, because now we are in the third quadrant. Okay, so these two formulas, oops, that should be a plural, these formulas should still be valid, even if we change the sign of r and theta. Okay. Oh, wait, I just did r equals is negative. Okay. So if theta is negative, okay, so let's say we're now in the fourth quadrant. Okay. And r is, let's keep it as positive. Okay. Then what's going to happen? Cosine theta will be positive if we're in the fourth quadrant. So r is positive, cosine theta positive, x stays positive. Okay. Sine theta is negative, r is positive. Okay, so therefore y is negative. And that's exactly what we expect in the fourth quadrant. All right, going backwards though, we saw that if you have the same point in Cartesian coordinates, you can have many, many values for r and theta. And in fact, they're infinite. Okay, but it's a good thing they're all related to each other. Okay, so it's just a Pythagorean theorem, basically. R is the hypotenuse of this right triangle. So r squared equals x squared plus y squared. And that takes into account the possibility that r is negative. Okay. Now, similarly, you have opposite over adjacent, y over x. That's tangent theta. Okay, as long as x is not 0. But if x is 0, it means you're on the y-axis. Okay, so therefore, your angle should be pi over 2, or you can add any integer multiple of pi. Okay, maybe you're at negative pi over 2, subtract pi, or 3 pi over 2, add pi. Okay. But truth be known, it's really just the first formula that we are going to find useful when we start integrating in polar coordinates in our next video. Okay, so this will be needed when we see functions that involve an expression like x squared plus y squared. All right, so for our last topic, we're going to look at what are called polar rectangles. Okay, we know what an ordinary rectangle looks like. Okay, but we're going to need to understand this because the domains for our double integrals will look like these figures over here. And these are all examples of what are called polar rectangles. Okay, so the notation for a polar rectangle is very similar for a regular rectangle. Okay, in fact, when you see the numbers here, you're going to say, oh, well, what's the big deal? What's the big difference? Okay, the big deal is this rectangle, this polar rectangle now means all the points are semicolon theta in R2, where your R coordinate is between A and B. And for simplicity, we'll assume that A is at least 0. Could be 0, but let's not make it negative. Okay, when we set up our double integrals, R will almost always be at least 0. Always be at least 0. Okay, let me remove that almost. Okay, similarly, our theta will be between the angles alpha and beta. Okay, and again, we have to think of alpha and beta in radians. Okay, so why are these shapes examples of polar rectangles? Okay, even though we do not call them polar rectangles, right? For heaven's sake, that is a circle. The edge is actually a circle. The whole region, which includes the interior, that is called a disk. Okay, and correspondingly, we have a half disk over here and a quarter disk over here. Okay, all of them have the same radius. Okay, radius of 2, 2, 2, 2. Okay, so why do we get this full circle? Our R is between 0 and 2. Theta is between 0 and 2 pi. So R goes from 0 to 2. Theta goes from 0 to 2 pi. Okay, so 0 to 2 pi. Yeah, we're basically going around the circle until we get back where we started. Okay, and similarly, if you only want the top half of the circle, of the disk rather, you change the terminal angle for theta to pi. Okay, so we now just go from 0 to pi. If you want only the quarter circle in the first quadrant, you go from 0 to pi over 2. Okay, but for all of them, our R is going from 0, the pole, to 2. Okay, so how about these polar rectangles? Okay, so this is called an annulus. Okay, so yeah, there's this thing that you throw. I think it's called an aerobie or whatnot. Okay, so it is made by removing a disk from a bigger disk. Okay, so so this time the R value will go from 2 to 3. All right, so we remove the part from 0 to 2. R only goes from 2 to 3. Theta, as before, goes around the circle 0 to 2 pi. Okay, let's skip to this one over here. Okay, if you only want the right half of your annulus, okay, simple way to do it is to restrict the angle from negative pi over 2 to positive pi over 2. Okay, and you might say, well, can't that be 3 pi over 2? I mean, you know, if you go counterclockwise, then that direction is 3 pi over 2. Sure, if you start at 3 pi over 2 though, you're not going to end at pi over 2. No. If you want to start at 3 pi over 2, you have to end at 5 pi over 2. You're adding pi to 3 pi over 2. Okay? Last one, save the best for last. Okay, so this is a portion of the full annulus where we begin with a theta of pi over 6, okay? And we end with a theta of 2 pi over 3, okay? Now, full disclosure, I drew these diagrams in GeoGebra, but not in polar coordinates, okay? I used ordinary Cartesian coordinates because GeoGebra can easily draw an inequality, okay? And it can also draw compound inequalities, okay? So for the first diagram, for example, I simply put in the inequality where x squared plus y squared is at most 4, okay? So that will give us the disk, all the parts within that circle. Okay, if I want this, I also include this symbol that's called a conjunction. Okay, that's the conjunction symbol. And I say, for example, here, and y is greater than 0 or equal to 0. Okay, so that will give you the upper half, right? So how did I draw, this annulus? Okay, so I said x squared plus y squared must be between 4 and 9, and x has to be greater than 0. Okay, this one is more complicated. Okay, so let's go to GeoGebra now, and I'll show you how to make these pictures. All right, so here's a fresh copy of GeoGebra, and let me show you. I believe we have used the curve command before, okay? However, I could be wrong. However, here we are going to enter a curve in polar form by putting another pair of parentheses here, and then we are going to put r and theta semicolon in between. Okay, let's start with a portion of a circle, okay? So let's say I want a radius of 3, and then semicolon, we'll put t as our parameter, okay? So you don't have to use the symbol theta, okay? GeoGebra doesn't care what character, what letter you use, okay? So t for theta, simple enough, okay? So curve, and then we will say theta will go from, out of the way, pi over 6, comma, pi. Ooh, okay, so as soon as I type in pi, okay, it's anticipating, okay, that it will go all the way pi, okay? But let's only go, let's say, to not pi, but 2 pi, oops, not 2 pi, but 2 pi over 3. Okay, so there you go. So that is the part of that annulus that I showed you earlier, okay, fragment of an annulus, okay? All right, now if you want a matching one, let's say at r equals 5, okay, the easiest thing to do, as far as I'm concerned, is to go duplicate input. Okay, so all we have to do now is change the 3 to 5, and there we go. Okay, so now there is the upper part of the fragment of our annulus. Okay, so now how would you complete the annulus? Well, you have the usual line segment command over here, which I'm not too crazy about because it creates auxiliary points, okay? So one thing that we can do is, again, to use the curve command to complete these line segments, okay? So this time we will have curve. Okay, so now theta will be a constant for this line segment, okay? It is the r, which will increase from 3 to 5. Okay, so we'll put r, semicolon, pi over 6 is our angle, comma, r will go from 3 to 5. Okay, there we go. So that is our segment, okay? And finally, we want this, so we will create a clone duplicate, and we will change the angle to 2 pi over 3. Okay, so there we go. That is our complete polar rectangle, okay, from r from 3 to 5, and theta from pi over 6 to pi over 3. Okay, I think I neglected to say an extra 2 there, from pi over 6 to 2 pi over 3. Pi over 3 is over here. All right, so just to finish off this video, I want to show you how I drew those diagrams using inequalities. Okay, so stay in Cartesian coordinates. Okay, if you want the full disk, for example, okay, let's just keep it simple for now. X to the power 2 plus y to the power 2 is less than or equal to, so you do need a keyboard for that, less than or equal to, and how about 16? Okay, so there you go. We have the disk of radius 4. Okay, if you want, let's see, we did the upper half, correct? What if you want the left half of this disk? Okay, so go back to the keyboard and then go to this funny looking thing over here. That's your symbols keyboard. Okay, so that's where you will find the conjunction. So we will also say, if you want to be on the left side of the disk, that means that y has to be less than or equal to 0. So I think we have to go to numeric, and yes, there it is, less than or equal to 0. But oops, I'm sorry, x. Why did I say y? Left half, x less than or equal to 0. There you go, my bad. Okay, later on, we are also going to, I believe we're going to have an integral example where the disk has radius 5. So let's make that 25, okay? And I want to be, let's say, above a horizontal line, okay? So I want to be where y is at least, okay? So I need to reverse this, go back to the keyboard, and then symbols greater than or equal to, oops, I'm sorry, just numeric, greater than or equal to 3. Okay, there it is. Okay, so we are going to look at a double integral where this is going to be our domain. Okay, all right, so that is part 1 of polar coordinates. I hope you enjoyed it. So in our next in our next video, we are going to see how to construct a double integral in polar coordinates, and we're going to compute them. All right, so until next time, I hope you enjoy the rest of your day. Bye-bye.